Okay, welcome back from your break. Dr. Matthew J. Traum here. We're working through applying the upper bound of the Niemi Principle um, to determine the correct number of metrics to apply to a down selection matrix um, to ensure ultimately that we have the right number of down selection matrices where every down selection matrix corresponds to a single subsystem, right? So ultimately, the correct number of subsystems is the end result of this overall process. So just a quick, if you're coming back to this video from a long break, what we just finished was working through a situation where we had metric 1 in this down selection matrix that had a very low weighting factor, right? 0.03, an order of magnitude lower than all the other ones and definitely less than 10% of the total. And so we went through this whole process of artificially maximizing its normalized value for the four concepts, and then artificially minimizing the value, normalized value for the four concepts, and then determining whether minimizing and maximizing those values changed the outcome at all. And we found that it didn't. And so we need to take corrective action, for example, removing the metric or changing the weighting factor. But what I wanted to show you guys is, this is just sort of a sanity check. If you do the same operation on one of the other metrics that has a much more reasonable and substantial weighting factor, you do get a situation where these ultimate values for the concepts, the selection values, change. So I just want to do a sanity check where I'm going to artificially normalize metric 2 to a maximum value, and we'll see what happens. Okay, so all I'm doing is taking this original down selection matrix, and I'm now looking at metric 2, and I'm changing these normalization values from 10, 8, 6, and 1, which is what they originally were, and I'm going to make them all 10. So 10, 10, 10, and 10. And then I'm going to recalculate the selection values for each concept. This one, well, it's unchanged because I started at 10 and ended at 10, so I get 6.74. This one I started at 8 and went to 10 for metric 2, so I get a change from 6.02 to 6.64. For this one, I went from 6 to 10, so I get a change from 5.87 to 7.06. And finally, I went from 1 to 10, and so my value goes from 2.23 up to 5.11. And what happens when we try to weight these, not try to weight them, try to rank order them to determine which one the down selection matrix has told us is the best. And recall, I intentionally set these up so that the matrix without any modification went from left to right, best, second best, third best, and worst in terms of those values. And then lo and behold, what's happened? Those numbers have switched around, right? So this guy, which was previously number 1, has gone to number 2. This guy, which was previously number 2, went to number 1. And this guy, which was previously number 3, this guy, which was previously number 3, went to number 1 here. And this guy, of course, remained unchanged because he was pretty low to begin with. But we've basically now got a reordering of the best to worst, whereas concept 1 was the one that I would have selected originally with nothing changed. Once I artificially normalized metric 2, concept 3 emerges as the winner. It's the best value. So what that tells me is that yes, by artificially normalizing metric 2 to its maximum value, it does actually influence the outcome of the down selection process, and so metric 2 should not be messed with. I shouldn't change anything with metric 2 because it is having an appropriate effect, meaning metric 2, which connects back to a customer need, is being appropriately considered and appropriately weighted by this down selection process. So that's good, at least for metric 2. But remember now, metric 1, we demonstrated that one had no influence regardless of whether we normalized the values to the maximum values or whether we made them the minimum values. It had no influence. And so we have to take some sort of corrective action. And there's sort of two things you can do in that case. So the first is that you can go back into your weighting factor calculation. Remember, you guys all know how to do that from a previous presentation. It's basically a democratic process where you guys are making a bunch of binary choices, and then you're averaging values, and then you're averaging the averages of the values across the group to get these weighting factors. So knowing that this happens, and knowing how insignificant metric 1 seems to be in this process, you might go through and just redo that exercise and see if maybe metric 1 could have a little bit more weight added to it to make it not irrelevant in this down selection process. So that's one, is just recalculating those weighting factors. And then the other possibility that you might do, if you guys have chosen the right value for metric 1 with respect to subsystem alpha, is just to remove it, right? It's not doing anything in the matrix, so you might as well take it out of the matrix, and it just reduces the complexity and reduces the amount of bookkeeping and tracking that you have to do. It will reduce confusion later for sure, but if you remove metric 1 from subsystem A, be sure that you haven't removed it from other matrices, that it appears in some other matrix and it is a significant factor. If it turns out to be a non-significant factor in every down selection matrix, you're effectively ignoring it in the overall design of the system, which you can't do because you won't be able to answer the customer's question, well, how did that particular customer need influence the design? So make sure that it's represented somewhere. Okay, so we've talked about this example of the metric weighting factor being too low, and then the final instance is if you just have too many metrics, and this is normally what happens, right, is people get overzealous and they want every single metric to be represented in every single subsystem, and so the end result is that you end up with too many metrics assigned to an individual subsystem. So again, just to remind you guys, ultimately what we're doing by applying the Niemi principle for the upper bound is identifying situations where one or more of the relevant matrices have no influence on the outcome, right? And so the same thing is going to happen here as happened in the previous example where the weighting factor was too low, in that if you have too many of these metrics, the value of each individual metric gets diluted to the point that individually they have no influence on the outcome. Okay, so let's go back here. All right. So here's my example. Again, I'm keeping this maybe overly simplified. You guys have got 12 concepts, but I've not filled in any of these values. I'm just showing you kind of the layout of the matrix. But I've given you an example down selection matrix where there are 9 different metrics, and that's probably too many, right? Because they're going to get diluted. And I did want to show you guys sort of where this rule of thumb, upper bound rule of thumb, came from, and this is where it comes from. I've just gone through and I've given these guys all equal weight, right? So there's 9 of them. They need to sum up to 100%. And so each one of them gets about, it's like 11.1% of the total weight factor, which is truncated here to just, 11%. And so ultimately, if we look at the next slide, each of these weighting factors is about 10%, a little over in this case, but about 10% of the value. And again, in this situation, I've made these all the same, right? When you guys go through your process of determining the weighting factors from your trade study, some of them are going to be slightly higher, some of them are going to be slightly lower. So the chances of all of these being the same value are basically 0. And you're going to have some that are down at 10%, 7%, 5%, and so forth. And those are definitely going to be less than 10% of the overall value. And so as we saw before, with the previous example, that's a situation that sort of cries out trouble in this case. So that's sort of where this rule of thumb comes from, right? Is if you just assign each of these the exact same value, you end up in a situation where each one is about 10%, and that's usually right on the lower threshold, the lower bound of where they can have any influence. And so we say 8 or fewer, and that gives us this rule of thumb. So that's where it comes from. Anyway, so I've showed you guys this slide. And when you're in this situation where you've got too many metrics and so the weighting factors are too diluted, what ends up happening is the exact same thing that happened before, is that one or more of them don't have any influence on the outcome. And so if you have 8 or 9 or more of these metrics in a single down selection matrix, you really don't need to go through the proof to demonstrate that yes, in fact, the weight factors do make them too diluted. That chances are that's true. And so you really do want to kind of break this up into 2 subsystems or more than 2 subsystems. And so the corrective action in this case, if you have too many metrics assigned to a single subsystem, is to break up that subsystem with too many metrics into 2 or more subsystems. And at least as a place to start, you want to make sure that each of those subsystems follows the Niemi principle. So you want to make sure that they have 3 or greater or 8 or less total metrics when you break this up. And some of these metrics might show up in 2 or multiple of those subsystem matrices. That's fine. But so long as you kind of break this up and you end up with 3 to 8 metrics in your kind of daughter subsystems, that should correct the problem. But if you have any doubt, of course, now you guys know how to go back and do evaluation of the weighting metric, and of course to determine what the right number of subsystems is. The right number of metrics is for the subsystem. So use those to kind of govern your selection of which metrics and how many metrics go into those subsystems. Okay, so that brings us to the end of this slide deck and this series of online videos. Thank you so much for your attention, and I will hopefully see you guys in class. Okay, take care.